Are there truths out there that will forever remain unknowable? Can mathematics have any input into this question one way or the other? In this TOKCAST, we're going to look at the limitations of mathematics and some more of the curious and surprising consequences of deductive systems. Perhaps you're having a drink while listening to this. I've got a cup of tea here with me at the moment. It's about a metre away from my hand. In order to pick up my tea for the next sip, I can think of my hand moving in steps like this. First, it moves half a metre towards the cup. Once that's done, I move my hand a quarter of a metre towards the cup. After that, an eighth, then a 16th, and so on. In other words, I can divide up the metre between my hand and the cup into an infinite number of ever smaller increments. Half of the distance, then half of what's left, then half of what's left of that, and so on. I would have an infinite series. A half, a quarter, an eighth, a 16th, a 32nd, and so on. This could go on forever. But if this sequence is infinite, even if the increments get ever smaller, it will take me an infinite amount of time to reach the cup because each step, howsoever small, will take some short amount of time to complete. And I don't have an infinite amount of time. Yet I can pick up the cup. How is this possible? Now, this supposed problem is called a paradox. It's obvious I can pick up the cup, and yet I've produced an argument that seems to be watertight. It must contain an error, however. But it turns out there are two solutions. One is mathematical. The other is physical. As we live in a physical world, the physical argument is the true solution in the actual world, and that solution is just this. According to quantum physics, you simply cannot divide up either space or time into infinitely small increments. There is actually a limit on how small space can be and how short time can be. The division of time will go on for a while, but eventually it will terminate at a shortest possible time. In fact, it stops at around 10 to the power of minus 34 seconds. This is known as the Planck time. So that's one solution. There is, however, also a purely mathematical solution as well. It says, it doesn't matter if you have a series made up of an infinite number of terms. You can add up all those terms and yet still get something less than infinity. If you do a higher level of mathematics, you might like to prove what the series a half plus a quarter plus an eighth plus a 16th onto infinity adds up to, or more rigorously, what the limiting sum of that series is. The answer happens to be 1. In other words, I can add up all those little fractions and still get a finite number. Remember, I started with something finite, a metre, and then basically argued for cutting my metre up into an infinite number of slices. I then tried to say that you couldn't take all of those slices and add them together again to get 1 metre. It's a bit slippery. This is essentially one of the paradoxes of Zeno. Zeno of Elea came up with these in ancient Greece in around 450 BC. Another of his arguments was about the tortoise and Achilles, and that's worth looking up. So what does this suggest? It suggests that deductive systems can sometimes turn up some really surprising results. In the case of the paradox just discussed, it seems like I had a watertight argument which deduced I could never pick up my cup. Of course, it turns out my argument was not a real paradox. But can you have real paradoxes in mathematics? Most definitely. We will see that paradoxical statements actually have consequences for the entirety of mathematics. First, a diversion into set theory, however. Most students of mathematics at some point encounter set theory in their senior years of high school. The idea of a set is simple. A set can be empty, or it can contain members. In fact, even primary school students can be taught the basics of set theory, using Venn diagrams. This sort of set theory allows for everything in the universe to be considered part of a big, universal set. We can talk about infinite sets or finite sets. The set of all positive integers is an infinite set. The set of all Prime Ministers of Australia is a finite set which has 26 members as of 2009. Perhaps you know some of the members.
Oh, fair shake of the sauce bottle, mate.
Now, does this idea of sets lead to any problems? Well, it turns out it does. Bertrand Russell, a British mathematician who was alive in the early to mid-20th century, and who we'll hear about more later on, raised a version of the following paradox. It is named for him and so is called Russell's paradox. The version I will give you is not exactly like Russell's own, but is the one which appears in most texts and resources on the internet. Let's begin. All libraries have catalogues. A catalogue is a list of all books in the library. Now imagine that the catalogue is a physical book, listing all the books in a particular library. Now most libraries have the practice of including a reference to the catalogue in the catalogue itself. After all, the catalogue itself is a book in the library, so it's written down in the catalogue. But I happen to know that my local library does not list the catalogue itself as an entry in the catalogue. The librarian thinks it would be silly to do so. After all, if you've got the catalogue in your hands, you don't need to look it up to find out if it's in the library or not. Okay, now stay with me on this. The most important library in Australia is called the National Library, and it's in Canberra. Now, the National Library keeps a record of all the library catalogues in the country. It actually has two catalogues of catalogues. The first contains all the catalogues which list themselves as members. The second contains all the catalogues which do not list themselves as members. The problem for the National Library is, where does the entry for the second catalogue go? Should we write its entry into the first catalogue? If we do this, then we are saying that it lists itself as a member. But that means we need to actually write down an entry for the second catalogue into the second catalogue. But once we do this, then we have an entry in the second catalogue that breaks the rules for the second catalogue. Namely, that it should list only those catalogues that do not list themselves as members. Now this is a genuine paradox. It's hard work and you may need to listen back over the last couple of minutes to appreciate it. There are notes to accompany this podcast, and they might help also. I see this particular paradox as a more intricate version of the liar paradox. The most trivial liar paradox is, this statement is a lie, or this statement is false. Now, consider that statement. Is it true or false? If it's asserting something true, then it's a lie. But if it's a lie, then it cannot be true.
Liar.
There are many versions of this paradox, and Russell's paradox also. The first such paradox that appears in Western philosophical writings is Epimenides' paradox. Epimenides was from Crete, and he wrote that all cretins are liars. It's not clear if he intended his statement to be paradoxical or not. Russell's paradox about sets is more succinctly expressed as, if S is the set of all sets that are not members of themselves, is S a member of S? Again, this is very tricky to get the first time you hear it, and for that reason we went to the National Library in Canberra. I hope that helped. To overcome these problems with set theory, mathematicians choose a set of rules to govern it. These rules are the foundation upon which set theory is built, and explain what can and what cannot be regarded as a set, and how it is possible to, for example, add two sets together or multiply one set by another. These rules in mathematics are called axioms. Axioms ideally should be consistent. They certainly shouldn't permit falsehoods or absurdity to be proved. It turns out you can define set theory in such a way as to avoid Russell's paradox and similar problems. Set theory that permits paradoxes is called naive set theory for this reason. So is that the end of the matter then? Just pick a set of rules which make paradoxes impossible? Then can we say mathematics will let us prove things as true? The problem, after all, is that a paradox shows that there is something lacking in your system of proof. If it permits paradoxes, then it seems like your foundations lead to nonsense. And this might mean your foundations are therefore nonsense themselves, and so the rest of what you end up proving might not be as certain as you hoped. So a proper choice of axioms can eliminate Russell's paradox. Well, yes, but it turns out there are bigger problems than this. the turn of the century, Bertrand Russell, whom I mentioned earlier, along with Alfred Whitehead, wrote a huge book called Principia Mathematica. In it, they set out to put all of mathematics on a firm logical footing. It was published in 1913, and it was all about the foundations of mathematics. It included the axioms of arithmetic, for example. It included axioms for other types of mathematics also, such as set theory. The question was, could you ever find a statement written down using the rules of mathematics that could never be proven or disproven? Well, in 1931, the answer was found, and it was found by one of the most brilliant mathematicians who ever lived. Kurt Gödel was a German mathematician who was born in 1906 in what is now the Czech Republic. By age 18, he had mastered university-level mathematics. In 1931, he published a paper which contained what are now known as Gödel's incompleteness theorems. They are possibly the most important theorems of mathematics discovered in the last 200 years. Gödel had to actually invent a new form of mathematical proof involving what is now known as Gödel numbering in order to establish his theorems. The proofs themselves are very deep and very complex and run to around 20 pages. You can actually buy them through Amazon.com in a little book. It seems like every second popular book on science and every popular book on mathematics mentions Gödel's incompleteness theorems. So what's the big deal about them? Firstly, the concepts of soundness and completeness. Soundness is the concept that a set of rules, logical or mathematical, permit only true statements to be proved. In other words, starting from the axioms, you cannot prove a falsehood. Completeness is effectively the mirror image of soundness. Completeness is about whether or not everything that is true within the system has a proof, or equivalently, whether for any given expression you can write down using the symbols of that system, whether that statement can be shown to be either true or false. There are lots of axiomatic systems. The most basic useful one is probably sentential calculus or sentential logic. It's the most basic type of logic. At school, if you're lucky, you might encounter a rarefied version of it. At university, if you take on a science or engineering course, it's hard to miss it. If you study philosophy or mathematics in any depth, you will likely take on one or more courses in logic. As for sentential logic, it can pretty easily be shown to be sound and complete. But for systems more complex than baby logic like this, it gets more interesting. Until Gödel, no one was really sure about normal, run-of-the-mill primary school counting-style arithmetic. Now, the rules or axioms of arithmetic are quite complex. The ones that are generally used, and which Gödel used, are called Peano's axioms, after the mathematician who first wrote them down. I mentioned them in the last TOKCAST. Gödel showed that arithmetic is sound. Everything that you can prove using the axioms is true, and you can't prove anything that's not. Okay, done. But what about completeness? Gödel showed that he could write down a statement that asserted its own impossibility of deciding as true or false. Again, to explain this fully takes the full arsenal of Gödel's proof, and is well beyond most, except perhaps those who've passed through a third-year university course on the topic. But to appreciate the idea is simple. Gödel essentially wrote down the mathematical equivalent of, "This statement is false," using the symbols of arithmetic. This statement is what is called undecidable. It suffers from all the paradoxical issues that we discussed earlier with sets that are not members of themselves, and the liar paradox. So what's the big deal? Well, that means that mathematics, even simple arithmetic, is not complete. There are statements in mathematics that are true, but which we can never prove as such. And there are statements which we can never decide as being either true or false. This is very significant. It has consequences for computer science, for example. No computer can be programmed which is able to once and for all solve all the problems of mathematics. There is thus no perfect calculator. This is probably a very good thing. It means mathematics will forever remain a creative exercise. Gödel himself was a troubled man, but he became friends with Einstein when he moved to Princeton University in the United States prior to the Second World War. Apparently, Gödel and Einstein would take long walks together at the Institute for Advanced Study where they both worked, with Einstein actually remarking that towards the end of his life, his own work there ceased to interest him very much, and instead he only went in order to have the privilege of walking home with Gödel. For Einstein's 70th birthday, Gödel's present to him was a set of paradoxical solutions to general relativity, which suggested the possibility of time travel to the past. Towards the end of his own life, Gödel was plagued with mental illness and became convinced that people were trying to poison him. He eventually starved himself to death and died in 1978. I did hear a story years ago that during their walks, Einstein would force Gödel to eat morning tea with him when he noticed how thin Gödel was. But I can't find any references now to this particular story and would appreciate it if someone could corroborate it for me. The significance of Gödel's incompleteness theorems are far-reaching. But like quantum theory and cosmology and any sufficiently complex human intellectual endeavour, it has been commandeered by some to push fringe or even pseudo-scientific claims. Often Gödel's proof is cited by relativist philosophers to bolster their claim that mathematics is unreliable. Without fully appreciating the significance of the theorem or understanding entirely the concept of completeness, you will nonetheless encounter pronouncements that Gödel's proof shows that mathematics is inconsistent. This is certainly not the case. It is also sometimes asserted that the incompleteness theorems have far-ranging consequences for the nature of the human mind. So the argument generally goes like this. Gödel's incompleteness theorem leads to the idea that if you have a system like a computer for proving theorems, let's say of arithmetic, then there will be statements that can be produced using the rules of that system which are true, but which nonetheless cannot be recognized as true by that system. This leads to the idea that the human mind cannot therefore be a mere machine or a computer. Because as a human, it seems to be inconceivable that one could be unable to judge as true a given theorem if it were actually true. This is an often repeated mantra of some who write popular science. At best, it is overreaching, while at worst, it's disingenuous. The fact is, we can produce any number of statements that are true and cannot be judged as such. Consider the following pronouncement. Barack Obama cannot consistently judge this statement to be true. Now, I can see the statement is true. You can see the statement is true. But despite its truth, Barack Obama cannot, however hard he tries, consistently judge it as true. Gödel's incompleteness theorems do not have any supernatural consequences. They say something quite strange and surprising about mathematics, but this does not mean that it then justifies everything strange and surprising about mathematics. It is strange and surprising that sometimes very smart people draw conclusions from science that really they aren't entitled to. Science and mathematics are fascinating, and we need not draw any conclusions about some of the amazing results we encounter in those fields unless we are compelled to by the evidence, be that scientific or in this case, mathematical. So there we have it, a TOKCAST about the limitations of mathematics. There will always be mathematical statements that even the techniques of mathematics won't be able to prove as true or false. It's not all mechanistic and impersonal, it's fascinating and requires a high level of creativity, and the only thing you should expect is to be continually surprised the deeper you look into mathematics.
For resources and links associated with TOKCAST, visit the TOKCAST website at www.tokcast.net.